Well, welcome to Math 152. Sorry we missed the first 2 days of class, but I don't want to get behind, so we're going to do this video. I'm going to have a few questions in the video that you're going to email me with the response to verify that you have watched this class, because I'm going to be continuing on as if assuming that you have watched the class, and if you don't, then you're already going to be behind and confused. So here's the course of study, which I can give you a copy when you come to class. This is Math 152. As you can see in the description, it's topics in functions, combinatorics, probability statistics, and algebraic systems. If I scroll down and I look at the schedule, you'll see we're going to start in chapter 10, then move to 11 and 12. We're going to actually expand chapter 12 material so that we don't have chapter 7 and 8 at the end. So we won't be doing the algebra review. We're going to talk about statistics in more detail. I'll let you read the course objectives. The text I've sent you an email about. You can buy this book online through Amazon. If you cannot afford the book is only going to be $10–15 because it's a used edition. If you can't afford it, I do have a limited number of texts that I can lend you for the semester, and then you can return to me at the end. So just let me know if you need one, and you can come by my office and get it. The office hours are, I pretty much have office hours every day, typically from 11 to 1. I have class till 11:15 on Tuesdays and Thursdays, so it's slightly different. 20% of the grade is associated with homework. So for homework, you should show a sufficient number of steps to be included in each problem. And don't just put the answers down. You need to show some work. I will collect the homework. I will assign the homework, and then I will collect it a week from the date of the assignment. So that gives you some flexibility. But don't get too lax, or you'll be way behind in homework. It's a reasonable amount of homework, but it's doable if you keep up to date. But if you try to do it all at one time, you're in trouble. So I want you to turn it in a week after I assign it. The grading is 5% is attendance, so we take attendance every day. Homework is 20%. So if you don't come to class and do your homework, you're already pretty much got a middle C, and there's probably not much chance that you can get a passing grade or a transferable grade. So if you stop attending, I may just withdraw you, because if I withdraw you early enough, then this grade doesn't count against you. But if I withdraw you, then there could be financial aid considerations. So the grading scale is a 10-point grading scale. As far as attendance is concerned, if you feel like you're going to miss a lot of classes, then I would suggest that you sign up for the online version of this class. If you're going to miss a few sessions, I do have recordings of the classes, the material in the classes, and you can watch those at another time. But more than a few days, then consider doing the online section. And then there's some additional information that I'll let you read by yourself regarding scholastic dishonesty and such, withdrawal policy, incompletes, and things like that. Okay, so we need to do the safety video and the Title IX videos. So please watch this.
Please remember, we can attempt to plan for many varied events. However, no planning or training is foolproof. Dabney S. Lancaster Community College in no way guarantees the unconditional safety of every student at all times. Critical incidents are many times dynamic and at times entirely unpredictable. This video offers no guarantees or claims as they relate to absolute safety and protection from a critical incident.
A critical incident can range from fire alarm activation, severe weather such as an approaching tornado, to reports of an active shooter on campus. Creating the best possible flow of information will assist in the best possible outcome and ensure safe, appropriate responses. Serious incidents, although highly unlikely, have unfortunately occurred throughout the nation.
Sirens blaring, police respond to a high school's call for help.
We have several notification tools to alert you of an incident. The two most obvious alarms are the external speakers and the classroom telephones. The external speakers are loud enough to be heard in most outdoor areas of the campus. The phone system produces an audible alarm and verbal notification of the campus emergency. In the event of an incident, a message should be broadcast over every phone on campus.
Attention. DSLCC main campus is under a lockdown at this time.
Please pay attention to messages and take them seriously. The DSLCC flat screen television monitors in the hallways will also generate an alert message. We ask that you take a moment and sign up for DSLCC Alert. The link can be found on the DSLCC homepage. DSLCC Alert will text your devices and send you emails to notify you about evolving incidents as well as weather and school closings. Familiarizing yourselves with the classroom and building emergency exit plans and procedures that are posted in your classrooms is a proactive approach to keeping safe. Study the exit routes. A planned exit may become unavailable to you, so familiarize yourself with alternatives. You've just witnessed a person walk onto your campus with a gun. Are you prepared to survive? Or are you going to allow your mind to talk you out of what you've just seen? Or are you going to take action and do something? Remember what you saw, and you must call 911.
So there's a shooter?
Do this while getting clear of the area. Warn people that you pass along the way of the danger.
An entire community trying to understand how a boy just crowned homecoming prince could launch such a violent attack.
You said we'd be shocked by or stunned by the number of ambulances and cop cars. Describe to us that scene when you were walking to the parking lot.
Dabney S. Lancaster Community College has always taken campus safety seriously, but in light of the recent increase in targeted campus violence, we want you to be prepared to survive. Please know that if such an incident occurs, law enforcement will be coming. However, in the very important time leading up to their arrival, we seek your determination for keeping yourself safe. Remember, if you can lock down, please do so. This remains one of the best courses of action. If locking down is not a viable option, we ask that you consider running and/or hiding. If these options are not feasible and you have no reasonable option left to protect yourself from harm, we support your decision to fight to protect yourself. Fight to escape. If at some point a law enforcement officer enters the room, do exactly what they say. Police may not know who the person at fault may be, so they must assume that everybody is a threat. If you are confronted by police, keep your hands visible. If they clear and secure your room and tell you to stay in place and not to leave, you need to stay until they come back for you.
Let me in! Let me in!
Remember, only through personal contact by campus officials will the lockdown be lifted. If anyone advises you to unlock the door, do not open the door. Police officers, administrators, and building monitors will have a key to open the door. Rooms will be released one at a time so people can be accounted for. Again, if a fire alarm is activated during a lockdown, stay in place. If you see or hear anything suspicious, let us know without delay. Inform an instructor, a staff member, or an administrator. Remember, if this is an emergency, dial 911. You will not get into trouble if you are wrong, and you might just save lives in the end. Are you prepared to survive?
Okay, so that is our safety video. So let's go look at the so the question for you is so when you send the email to tell me that you watched this video, what you need to do is tell me be prepared to what based on that video. Be prepared to, there's a word. Okay, so here's the training for the
What is Title IX? Title IX is a federal civil rights law that prohibits sex discrimination in educational programs, activities, admission, and employment. Sex discrimination includes sexual violence and sexual harassment.
Under DSLCC Title IX and Sexual Misconduct Policy, DSLCC prohibits the offenses of domestic and dating violence, sexual assault, and stalking. Some examples of sexual misconduct include name-calling, inappropriate touching, groping, whistling, sexual assault, sexting, telling lewd jokes, requests for sexual favors, pinching, poking, sexual violence, rape, and dating violence. Definitions of sexual harassment, sexual violence, domestic violence, dating violence, and stalking can be found in the Title IX policy. If you or someone you know has been a victim of sexual misconduct, there are resources to help you. Title IX Coordinator April Tolley and Deputy Title IX Coordinator Dr. Matthew McGraw. You may also report online or report to any member on the DSLCC Threat Assessment Team.
DSLCC is responsible for conducting adequate, reliable, and impartial investigations of reports and complaints of sexual misconduct. To ensure the safety and health of everyone on campus, DSLCC employees are required to report information they receive to the Title IX coordinator.
We will keep your information as private as possible, however, we cannot guarantee confidentiality.
Retaliation against anyone who reports sexual misconduct is strictly prohibited. Anyone responsible for retaliation will be subject to disciplinary action.
If you would like to talk to someone confidentially, you may contact Safe Home Systems Incorporated, Project Horizon, or National Domestic Violence.
Speaking to a confidential resource is not the same as reporting the complaint to the Title IX coordinator. If you suffer from severe injuries, call 911 immediately.
created using Powtoon.
Okay, so that is the Title IX video in it, and I want you to put in your email to me that you watched it, and just to reiterate that faculty must report any knowledge of sexual harassment, sexual assault, and we cannot be confidential. We cannot be confidential about that. We have to report it. There are confidential resources that are available, and we can point you towards those. But if you tell us anything, we have to pass that on. Just that's the law. Okay. So that is it for the introductions, and now we'll talk about the class. We can start the class. And I'm going to ask you one more question during this video that you'll also include, just to verify that you've been listening to what I have to say. Okay, let me see how much time I've spent so far. 21 minutes. Okay, so let's move on. So we're starting chapter 10, and actually what I want to do is I want to just kind of give you an idea of where we're going with all this. So chapter 10 is called Counting Methods. It's just a way of looking at you know, the number of different ways certain items can be arranged. So there's things called combinations and permutations, and as an example, if you had 10 people, how many ways could you choose 2 people to be president or vice president for a club? And you can use counting methods to determine that. So that we need that skill to be able to then talk about probability. And probability initially was of interest mostly because it helped people who gambled figure out, you know, what the odds were of winning certain games, which, you know, is interesting, but doesn't have much social significance to it. So there are probabilities, you know, in terms of, you know, what is the chances of, you know, beyond games, just beyond playing the lottery. You know, what's the probability of me winning the lottery? And probably the biggest one is its significance in statistics. Now, there's 2 branches of statistics. One's called descriptive statistics, and that's just presenting the data, looking at where the average value is. People know the word average. And then there's something called standard deviation, which means how close to the average value is the data. Is it spread out, or is it close, more compact? There's also a branch of statistics called inferential statistics. Now in the past, this class has only talked about descriptive statistics. What I'm going to attempt to do here, instead of talking about algebra at the end, I'm going to talk about inferential statistics in chapter 12, or as a part of chapter 12, or it may actually be a separate section. I'll provide some material for you. So those all kind of group together. And the final topic we have is personal finance, which, you know, as a teenager or 20-something-year-old, you know, initially you're probably going to, I don't need to know this, but my daughters, who are 31 and 35 or 36, they've specifically said to me, I wish they taught that to me in high school. And the question is, if you teach it, will you pay attention? So hopefully I can instill in you the desire to pay attention, because when you start to think about retirement and buying houses and all the financial things in your life, it's good to know these things so they're just not a big surprise, and they can make the difference between a comfortable retirement or just struggling to get by. Okay, so chapter 10, counting methods. So what we're going to do first is we're going to do section 1, which is just kind of the rudimentary idea of how do you count things, how do you figure out how many ways something can be arranged. We'll start with just how many ways can so many be basically, well, let's keep going on. Don't get carried away here. Okay, so non-trivial counting, which means more than looking at a number of people and just counting how many there are, usually requires a multi-step or a multi-part process. And during each part or process or step, there are so many choices that you can make, so many options available. And you can find the total number of options by multiplying together the number of options in each step. So we're going to start with the simplest case, which is a one-step process, or we'll call it a one-part task. So let's look at this example. Considering we have a club N with 5 members, and the members of this club are Alan, Bill, Kathy, David, and Evelyn. The question is, in how many ways can this group select a president? So there's one step in this question. Select a president. So if you were to select a president, then you look at the number of people, and you could say, well, I could pick Alan to be president, I could pick Bill to be president, Kathy to be president, David to be president, and Evelyn to be president. So there are 5 ways. So the answer to that question is 5. So that's a one-step process. Now a 2-step process would be, how many ways can I select a president and a vice president where the same person cannot be both president and vice president? We'll get to that kind of thing in a little while. So here's some other, one-step processes. If I flip a coin, how many ways, what are the number of outcomes that I can have for flipping a coin? Well, the answer is 2. It can be heads or tails. How about rolling a dice? Well, the dice is a cube and it has 6 sides, so there are 6 possibilities of rolling a dice. How about picking a card out of a deck of cards? Well, there are 52 cards in a deck, so there are 52 possibilities if all I'm doing is picking a card. So these are all one-step processes. Now, what about if I have a 2-step process? Well, we'll get to the details of that, but that's, how many ways, if I fill up a coin 5 times, how many ways can I end up with heads or tails? One possibility would get heads every time, one would be get tails every time, then you could get 1 head by doing it first flip, second flip, third flip, fourth flip, fifth flip. We're not going to get to that. We'll get to that, but right now we're just talking about one-step processes. And if you do these things more than one time, then this is a 2-step process. Okay, so here's a question. If we roll a red dice and a green dice, how many possible results are there if you don't allow repeats? So the way you, what we're assuming is the dice has 1 on one side, 2 on the second side, 2 dots, 3 dots on one third side, 4 dots on the fourth side, 5 dots on the fifth side, and 6 dots on the sixth side. So, this is called, it's called counting by systematic listing. So the way we would do this is we would come up with some organized way, and one way is to, and here we have actually 2-part task. We're going to roll a red dice and we're going to roll a green dice. So we want to come up with some systematic way of coming up with all the different possibilities. And what it means when it says repeats is it means that 1 on a red and 1 on a green doesn't count. So if you have 1 on a red and a 2 on a green, and then a 2 on a red and a 1 on a green, those are not repeats because they're different different numbers. Okay, so what we're going to do is we're going to list all the possibilities, and then we'll limit it based upon the description that they're talking about. So what I'm going to show here is here's the green dice, there are 6 possible sides. Here's the red dice, there's 6 possible sides. In these squares, I'm going to write the first number will be the value of the red dice, and the second number will be the green dice. So that's the red dice is 1, the green dice is 2. The red dice is 1, the green dice is 3. The red dice is 1, the green dice is 4. And you can see, you know, once I establish a pattern, I can start going down. So the first number is 1, the second number is 1, 2, 3, 4, 5, 6. And then we go to the next row. We can get a 2 on the red dice. So all of these have 2 on the red dice. And then the second dice can be 1, 2, 1, 2, carried away there, 2, 3, 4, 5, 6. Then you change the first number to 3, and you do that again. And then the first dice can be, the red dice can be a 4. So it's just like basically writing out numbers here. 2-digit numbers, where the first digit can be a 1 through 6, and the second digit can be 1 through 6. And I have you do something like this. And again, yeah, don't chew gum and walk at the same time here. And the final one. So these are all the possible combinations. Did it again. Of red and green dice. Okay, so those are all the possible ones. Now, how many possible results are there if we don't allow repeats? So these are the ones that I don't count. These are repeats. So if you take the number of rows times the number of columns times the number of rows, you'll get 36, and 6 of those I'm going to eliminate. So the answer is there are 36 minus 6, or 30 possible results. Now if I said how many possible results are there if we allow repeats, then if we said allow, then the answer would be 36. Okay. But the key thing is we've made a table up so that we have a systematic approach to listing all the possibilities and then eliminating the ones that don't apply to our particular question. Okay, now it says, what about if the order of numbers is not important? So that's a good question. So let's go back, because this, yeah, I was wondering about this when I was doing it. So the question is allowing repeats, and it depends on how you define repeats in this case. So if you say repeat numbers, then those would be, I'd eliminate those. So we're going to actually talk about 2 different cases here. So let me just another way. Let me just put a what's another definition of repeats? Well, a repeat would be 1, 2, or 2, 1. It has the same 2 numbers. They're just in a different order. So if we use that definition of repeats, then these we would include these diagonal ones because they're only seen one time. And then what you would do is you would eliminate this one because that would be a repeat of that one if order is not important. It's kind of like lottery numbers. For lottery tickets, it doesn't matter what the order is. Order is not important. So this is matched by that one, and also all the ones that are above this diagonal are matched by ones below the diagonal. So I would eliminate all of these. Okay, so all of these have ones that are the same 2 numbers. So let me just pick one here, like 34. That's 43 is the one that matches that in terms of the numbers. So using this definition of repeats, then I would eliminate those, and I forgot one right here. So how many does that leave me with? So you'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So the answer would be 21 possible results. So what we did here is we said repeats were 1, 1, 2, 2, 3, 3, 3, 4, 4. If you define repeats as the numbers, same numbers but a different order, then you would have 21 possible results. But it all went down to the original table, which listed all the possibilities. So when this next thing says how about if the order of the numbers is not important, then if the order of the numbers is important or not important, if the order is important, then you would include every one of them because they wouldn't be repeats anymore. So if order is important, there are 36 possibilities. If order isn't important, then we have 21 possible results. Okay, let's look at another example. So how many possible results do we have if we add the two dice together? So that's usually when you're playing some kind of dice game. You roll two dice, you add them together, and each one has a result depending on the game. So to fill out this table, instead of putting 1, 1 in this space, what I do is add these two together. So the result is the addition of the two. So 1 plus 1 is 2, 1 plus 2 is 3, 3 plus 1 is 4, and you can see I just continue to write out. Here we have the same thing. We have 2 plus 1 is 3, 2 plus 2 is 4, and then you just can continue on. And so, you know, this whole table can be filled out as such. So now 4 plus 4 is 8. See how it fits in. Okay, so that's the systematic listing, and the question is how many different sums can I end up with? Well, this specific question they asked here was what is the how many combinations have a sum where they add up to either 3, 6, 9, or 12. So I go up to my my table and I say, okay, how many have 3 as a sum? Well, I've got these two entries, so there's 2 of those. How many have 6 as a sum? 1, 2, 3, 4, 5. So there are 5 that have 6 as a sum. 9, 1, 2, 3, 4. 4 that have a sum of 9. And there's 1 that has a sum of 12. And so 2 plus 5 is 7. 7 plus 4 is 11. Plus 1 is 12. So there are 12 combinations where the sum is equal to either 3 or 6 or 9 or 12. You know, you could ask the question, how many different sums are possible? And you'd say, well, the possible sums are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 different sums that you can get. The most likely one is 7, and the least likely ones are 2 and 12. Okay, final example here is creating 2-digit numbers with a limited number of numbers that we can use for the 2 digits. And you can't, well, 0 is not an option, so we don't have to worry about that case. So again, what you would do here, you don't add these together because they're asking for 2-digit numbers. So you would have this one be your, this, you could break this up. This would be the first digit, and this would be the second digit along this line. So the first digit is 1, second digit is 1, first digit is 1, second digit is 6, first digit 1, second digit is 7, and just continue on here where the first number is the one in the row and the second number is the one in the column. So the answer is 16. The blue here, there are 16 two-digit numbers. Now that's if we can repeat them. So again, you have to read the problem carefully. So let's answer two questions here. There are 16 two-digit numbers that can be formed from the numbers in this set 1, 6, 7, 9. And there they are. They're listed in that table. Now if you don't allow repeating digits, so 1, 1, 6, 6, 7, 7, 9, 9, if you say that's the question, there are 12 two-digit numbers that can be formed without repeating the same digit in both places. $61, $71, $91, $96, $76, $16, $17, $67, $79, $69, it's 19. There are 4 even numbers. 16, 66, 76, 96. There are 12 odd numbers. So again, the table allows us to create all of the possible two-digit numbers, and depending upon what they're asking specifically, then we may eliminate some of them from our choices. Okay, so that's numbers, flipping dice, and that's using tables to come up with the number of possibilities. The second thing we're going to talk about are tree diagrams for multi-part tasks. The main thing that we're going to look at is flipping a coin. Now there's, I think, some examples in the book which look at light switching. You could also do it for things like choosing officers in a club. At some point the size becomes an issue. One thing to point out is this, what we're learning here is we're finding out the number of those occurrences, and we're also listing all the occurrences so we know what they are. So if a coin is flipped 4 times, what are the number of possible combinations of heads and tails? And the order is important. So if we get heads, tails, 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 and then tails, 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 heads, those are different because the order is different. So the way you do this is you have a 4-step process. We flip the coin 4 times. So this is a 4-step process. Each step there are two possible outcomes. So step 1, step 2, step 3, and the results of each step are independent of what happens in the previous step. So the first step is you flip a coin, and we get two possibilities. You can either be a true or not true or false, but a heads or tails. Heads, tails. Now, once the first one's a heads and we flip a coin, the same coin or a different coin, doesn't matter, there are two possibilities in the second step. They can be heads or tails. If we get a tails for the first time, there are two possibilities, heads or tails. It's a completely random process. Then finally, the next step, you can see why it's called a tree diagram, because we're drawing like branches of a tree. So, third step, there are two choices, heads or tails, heads or tails, heads or tails. So each one of these represents the fourth step. These previous things are representing what happened in the previous step. And then finally you can go step 4, and each one of these branches out again. Okay, so you have heads, tails, 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 heads, tails. If we had 5 steps, we do it again. So those represent all the possible ways that you can flip a coin 4 times, where the order is important. And the way you could list these is you could just follow each, start at the root here, and then follow each branch. So if I just follow this top branch, I'll have heads for the first, heads for the second, heads for the third, heads for the fourth. So I can show that by listing it as such. First letter is the first flip, second letter is the second flip, third letter is the third flip, fourth letter is the fourth flip. So that's this one. Then I can go all the way up here. Instead of going straight up, I go down. So that is represented by heads, 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 tails. Okay, then the next option would be, instead of going up here, because we've already got those two, is to then come down here and then go back up here. So this heads, heads, tails, heads. And then you go heads, heads, tails, tails. So that gets those first 4. Then we go down to the next one. So the next option would be where the second one is tails, heads, tails, and then you go heads, heads. And I'm just going to write the rest of these out. And at this point you'll see we have 8. So those count heads, tails, 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 heads, tails, tails, tails. And then you can go to the next one, and really the only thing that happens is the first letter becomes a tails, and then the last part kind of repeats itself. So I just take the last 3 that I have here and just replace the first one with the tails. And you can see I've got 8. Well, I've got 7. I'm missing one here. What did I do? Okay, I think I got to take this one and move it down a little bit. Don't know why it didn't let me group that thing. Group. Okay, so let's make sure I got this in the right place. This is actually, this one's this one right here. So I've got tails. Okay, I've got tails. I've got tails. Some places heads with the tails. And tails, heads, tails, tails, heads, tails, tails, tails. Okay, so now we have 8 more. So you see, there's a total of 16 different arrangements. And if you took first semester and I replaced heads with trues and tails with falses, you would see it looks very similar to the truth table, the way we did truth tables. So what I'm going to do is I'm going to take, oops, didn't mean to do that. I'm going to take all these, I'm going to put them down here just to make it all in one row. And what you would see is that the first value is heads for 8, then tails for 8. Then the second one we have 4 heads, 4 tails, 4 heads, 4 tails, and then you have 2 heads, 2 tails, 2 heads, 2 tails, 2 heads, 2 tails. It's just confirming that I did everything right. 2 heads, 2 tails, and then the last letter is heads, tails, 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 heads, tails. So those give us the. So I did it originally by using this tree diagram. The other, this kind of way that I just double checked it is what we call systematic listing. So I came up with a systematic approach to looking at all the different ways that these coins could result in heads or tails. Now we're going to just say it's something that's kind of a little ahead of what we'll do, but you know, what's the probability of me getting all heads, flipping a coin 4 times and getting all heads? And the answer would be, probability be 1 divided by 16, because there's, out of these 16 different possibilities, there's only one case that is all heads. So the probability would be 1 over 16, or whatever the decimal equivalent to that is. Now, how many tosses have at least 3 heads? So once you've gotten this thing listed out, you can answer a lot of questions. At least 3 heads. So you got to be careful. One question would be, let's write both of these down. How many tosses have exactly 3 heads? So you could go through here and look, exactly 3 heads. That one has 1, 2, 3 exactly. This one has exactly 3 heads. This one has exactly 3 heads. This one has exactly 3 heads. And I think that's it. All the other ones just have 2 heads. So there are 4. 1, 2, 3, 4. And you can kind of see what happens. The tails here, tails there, tails there, tails there, and the other head, the rest of them are heads. So how many exactly have 4? There are 4 that have exactly 3 heads. How many have at least 3 heads? Well, we add one more to that, because this has at least 3 heads. It actually has 4 heads, but at least means basically 3. How many has greater than or equal to 3? That's kind of the same with a list, at least. So in this case, the answer is 5. There are 5 that have at least 3 heads. There are 4 that have exactly 3 heads. Then you could look at exactly 2 heads, and that's one that's going to have the most. So let's just look at that question. Exactly 1 head, or 0 heads, 1 head, 2 heads, 3 heads, 4 heads, and those are our choices. Okay, so we said there were 5 that had exactly 3 heads. There's 1 that has exactly 4 heads. There's 1 that has exactly 0 heads. Turns out there are 5 that have exactly 1 head. Is that true? No. This was a 4. I don't know where I got the 4 from. So there were 4 that had exactly 3 heads. There's 4 that have exactly 1 head. You can see that here. This which ones? The ones down here. This has 1 head. This has 1 head. This has 1 head. And there's one other one. This has 1 head. So those are 4. And it turns out there are 6 that have exactly 2 heads. And if we add those all up, 1 plus 4 is 5. 5 plus 6 is 11. 11 plus 5 is 14. That's 16. Okay, we have 16 total possibilities. One has 0 heads. One has 4 heads. 4 have 1 or 3 heads. You can see the symmetry, which is not surprising. Okay, so we're going to do the same thing here with a club. We're going to use, this is going to be using a tree diagram. Count the different ways a president, secretary, and treasurer can be chosen if the president and treasurer must be women. Okay. So it's a 3-step process. President. Choose a president. Choose a secretary. Secretary and treasurer. Okay, so that's step 1, step 2, step 3. And you may think, well, does it matter which order I do these? Does it matter if I choose secretary first or treasurer in terms of? And the answer is no, in terms of the number of different possibilities. Okay, so when you choose a president, president has to be a woman. So we look in here, we have 2 choices. So when we make the choice for president, it's either Kathy or it's Oprah. No, Evelyn. Okay. Now, because there are only 2 women, one has to be president, one has to be secretary. I mean, it has to be treasurer. So when we choose a secretary, it's going to have to be a man, or we're not going to have enough people to do it. So what we have, instead of 2 options here, we have 3 options. We have Bill, Alan. I should have done alphabetically, but it doesn't really matter. David. Likewise, if we choose Evelyn, the number of choices we have. The choices we have are Bill, Alan, and David. And then finally, when we've picked Kathy as president and Bill as secretary, there's 1 woman left, which is Evelyn. So Evelyn's the one that's left over here, and she, by default, gets the treasurer job. And over here, Evelyn's been chosen as president, so Kathy is the option for treasurer. And so from this tree diagram, we can write out the different options. So we have C, Kathy, Bill, Evelyn. We have Kathy, Alan, Evelyn. We have Kathy, David, Evelyn. And then from this one, we have Evelyn, Bill, Kathy, Evelyn, Kathy, Evelyn, David, Kathy. So those are the possibilities, and so you just count them. 1, 2, 3, 4, 5, 6. 6. So to answer the question, count the different ways a president, secretary, and treasurer can be chosen if the president and the treasurer must be women. And the answer is 6, and these are the different choices. So, systematic approaches: lists, tables, tree diagrams. Now, as our last example, how many 3-digit numbers have the sum of their digits as 22? So this is not quite as straightforward. You just kind of have to think about it. And the best thing to do is to just pick up a 3-digit number and see what happens. So I'm going to start with 9, and so that's the first digit, and then I have 9 as the second digit. And the third digit is set. There's only one choice here, which is 9 plus 9 is 18, so 4 would be the final digit so that this is satisfied. So what I can do is kind of start a tree diagram. So 9 is definitely a possibility. So this is step 1, is to pick the first digit, which is the hundreds digit, and then we can pick the tens digit, and then we can finally pick the ones digit to make it work out. So for 9, the options are 9, 8, 7, 6. So let's just see what happens here. Now if I choose a 9 and a 9 here, that's 18, so that's 4. If I choose 9 and 8, that's a 5. 9 plus 8 is 17. 17 plus 5 is 22. So this one's going to be 6, 7. So I've got 95, 95, and then that would have to be an 8. And then 4. And that would have to be a 9. And you see that's as far as I can go, because if I go to a 3, I'd have to put 10 in there, and that's not a digit, single digit, that's 2 digits. So that's 9. Now, you know, if I do 8, and again I can choose 9 as a second digit, just like I did here. 8 plus 9 is 17. 17 plus 5 is 21, 22. And again, so I'm going to be able to do this all the way down to 5 instead of 4, and you'll see why in just a second. So that's 6, 5. Okay, so 8 plus 8 is 16, plus 6 is 22, 8 plus 7 is 15, plus 7 is 22, 8 plus 6 is 14, plus 8 is 22, and 8 plus 5 is 13, plus 9. So you can see I've got one less choice there, and you can see it, you know, a lot of times you can establish patterns. That's why people good at seeing patterns can do well at math. So I could keep going using the same logic, but I could just say, well, I see this pattern that's going to happen. So let's double check it. 7 plus 6 is 13, 13 plus 9 is 22. Okay. First digits is 6, 9. This was 6, so that becomes 7, 7, 8, or 6, 8, 8, 6, 7, 9. So again, I've got one less. You know, started with 6 numbers, 5 numbers, 4 numbers, 3 numbers. So I've got 5 and 9 and 8. 5 and 8 and 9, and then the last one would be 4 and 9 and 9. So this is kind of like a tree diagram, and then I could, you know, I could list all of these: 994, 985, 976, 965. That went the wrong way. I was trying to see a pattern. I got confused. 958, 949. Then you go to the next one, 895, 886, 877, 868, 859, 796, 787, 778, 769, 697, 688, 679, 598, 589, and then 499. 6, 5, 4, 3, 2, 1. I didn't scroll down because I was kind of, once I came up with this pattern, then I kind of knew what to do. So I've got 6 here, I've got 5 there, I've got 4 there, 3, 2, 1. So the answer to this question is you add these numbers together, So that's 11, 15, 18, 20, 21. So there are 21 different 3-digit numbers whose digits add up to be 22. And there's your homework assignment for section 1. So these are due a week from the time I assigned them. So since we missed the first day of class, but you only meet twice a week, so let's have these. These will be due for the Monday class. They'll be due next Monday, and for the Tuesday class, they'll be next Tuesday. And of course, you're going to say, well, the Monday class doesn't meet on Monday, so that means they're due on Wednesday. Okay, so we're got just a few more minutes, so we're gonna, if you need to stop this recording, get those, go ahead. Let me go ahead and save this. So that's systematic listing. So we'll go to the next section, which is section 2. Okay, so what we want to do now is we want to come up with a method of coming up with the answers to these questions without having to list using lists or tree diagrams. And it's using what's called the fundamental counting principle. Now, before we define what the fundamental counting principle is, we need to define something else. So let's go to the next page. So, what if we were just interested in the number of possibilities rather than the exact choices? Then there might be an easier way. And there is. So there's this thing called the uniformity criterion for multi-part tasks. And it says a multiple part task is said to satisfy the uniformity criterion if the number of choices for any particular part is the same no matter which choices were selected for the previous parts. We kind of use that when we flip the coin. It didn't matter whether we got heads or tails in the previous flip. There were still 2 options. Even when we chose president, treasurer, and secretary, there were 2. When we chose a president, there were 2 choices. When we got to choosing a treasurer, there was only 1 choice because we had already chosen that. So to be able to use the fundamental accounting principle, the uniformity criteria has to apply, and pretty much anything that we're going to do, it will apply. So you probably won't have to make that choice. Okay, so here's the fundamental accounting principle. When a task consists of k separate parts and satisfies the uniformity criterion, if the first part can be done in n sub 1 ways, the second part can be done in n sub 2 ways, and so on through the kth part, which can be done n sub k ways, then the total number of ways to complete the task is given by the product of all of those subscripted variables. So the subscript just refers to which part of the process or which step of the process. And this is making it general so it can have any number of steps. Most processes don't have huge amounts of steps, but like flipping a coin, n sub 1 would be how many ways can I get a flip a coin? Well, n sub 1 would be 2 when I flip the coin the first time. N sub 2 would be 2 because it's the same coin or the same kind of coin, and so forth and so on. And if you multiply those numbers together, you get the final total number of choices. So since we just talked about the flipping a coin, we flipped a coin 4 times, and we found out there were 16 possibilities. So, flipping a coin. The question that I want you to answer is, do you still have to take Math 150? Do you still have 151 or 152 to remaining to take after you finish this semester? Are you done with math? So that's the question I need for you to answer. 4 times. So there's n sub 1 equals 2, heads or tails. N sub 2, that's the second flip. There are 2 results, heads or tails. N sub 3 equals 2, heads or tails. And n sub 4 equals 2, heads or tails. Those are my possible choices, possible outcomes. So it says if you have a 4-step process, so we'll just say the number of arrangements. Of this 4-step process is going to be equal to n sub 1, which is 2, times n sub 2, which is 2, times n sub 3, which is 3, times n sub 4, which is 2. 2 times 2 times 2 times 2 is 16. That's exactly the number we got. Now, I didn't list all the possibilities, you know, all heads, all tails, all that kind of stuff. But if all we want to know is what are the number of arrangements, then we can use the fundamental counting principle to simplify the process. Okay. If you do a coin 5 times, you just have one more 2 added, multiplied, so there's 32 different ways that you can have. So here we're doing the fundamental counting principle would say n sub 1 through n sub 5 is the number 2, and you multiply 2 by itself 5 times, you get 32. Okay. How many ways can you group these 5 people where order is important? So there's like a 5-step process. You've got 5 slots to put them in. And so when you go to put somebody in the first slot here, how many people do I have to choose from? Well, there are 5 people to choose from. Any one of these people can go in the first slot. So in this case, n sub 1 is 5. Now, when you've put somebody in there, you know, let's say I stick Alan in there. Well, Alan's no longer, you can't choose Alan anymore because he's already in there. Or anybody, whoever you choose, is not available. So generically speaking, for the second choice, putting this person in the second slot is there's only 4 people. And you can do the same thing. So each time, because you can't put the same person into more than one slot, you see each time you pick somebody, another person, they're not available for the next space. And so that's my 5-step process. And so you multiply those together. 5 times 4 is 20, times 3 is 60, times 2 is 20. So there are 120 possible ways to order 5 people where order is important. Now, if order wasn't important, then there's basically, you know, you could have any arrangement, and there'd be only one way. You just put everybody in some slot. And that's kind of the difference between permutations and combinations. Permutations is where order is important. Combinations is where order is not important. Okay, so I think we'll stop there, and we'll pick up on that on Wednesday and Thursday, depending upon which class you guys are in.